Thanks for the kind intro and for the invite. Yeah, so I'll be describing tensor network, or an algebraic common language that we've derived between the two fields of many-body quantum physics and deep learning. It's based on a line of works. Approximately half of them are oriented towards a better understanding of the operation of deep learning architectures by using tools from the many-body quantum physics regime, and around half are oriented in the other direction to a better understanding of many-body quantum phenomena by using deep learning tools. So to start off, I'll make the point that though these are two distinct scientific disciplines, they share a common need for what we call many-object expressiveness. So in the machine learning side, you guys can imagine that in order to intake this array of pixels, black and white pixels, and tell us that this is a cat and not a dog, the architecture needs to implement some sort of a convoluted function over the pixels. And similarly, a language model predicting the next word in a sentence needs to intake many inputs, the previous words, and make a prediction. In the physics domain, a many-body quantum system is an array of quantum particles interacting with each other, and they have what they call quantum wave functions that should and indeed encapsulate all the quantum information about these interparticle dependencies. So we'll make the case in this talk about some sort of a mathematical equivalence that will be clearer between the pixels and particles, which will allow us to use the tool of quantum entanglement, which is a measure of dependencies between quantum particles, as a measure of dependencies that deep learning architectures implement with respect to their inputs. So we'll see how that comes about. Now, tools from the two domains are different. We have convnets, RNNs, etc. on the deep learning side, and tensor networks in the physics side is a leading tool to simulate many-body quantum systems. But we will be looking at all of these tools just as multivariate functions, and that will allow us to borrow tools and concepts and methods and also results from one domain and address the other. And generally, the approach is to rely on strengths in each domain and address gaps or weaknesses in the other. So in machine learning, it's obvious that we have now these very strong architectures that have solved hard problems in machine learning in the past several years. And in physics, there's actually a need for such strong computational tools, because there are currently unattainable quantum phenomena, mostly in 2 and 3 dimensions. So a lot of what's solvable now in many-body quantum physics is only 1D systems, which are far from reality. And there's a strong need there for powerful architectures. And we show that deep learning architectures are fit more than any other architecture for these tasks, and we actually apply them to such investigations of quantum phenomena. In the other direction, in the physics, they have an advantage of decades of theoretical development. So tensor networks, which we will use, have been around for a decade and a half, but more fundamentally, the concept of quantum entanglement is around for nearly a century, and we use results derived there in order to better the understanding of how the architecture, the convnet or the RNN architecture, can be tailored with respect to a certain task's input. Okay, so we'll start by drawing an analogy between a set of convolutional and recurrent arithmetic networks, which are theoretically accessible surrogates of the common convnets and RNNs. I'll give a motivation slide of why they're interesting, and then we'll describe them. So they're called arithmetic circuits, and they allowed previously for functional analysis, measure theory, and tensorial analysis tools. And in this line of work, we obviously add quantum physics, but also graph theory and combinatorics. But beyond being great theoretical entities, they also work well in practice, and theoretical conclusions attained on them were shown to extend to the practical setting of convnets and RNNs. So that's sort of a motivation, and we'll see the architecture. So the convolutional arithmetic circuit is a regular convnet in that there are inputs, n pixels in an input image, and you give some sort of prediction. It could be a class score, for example, at the end. And in the middle, there are L hidden layers performing convolutional operation. The difference from the common setting is that the activations, usually a ReLU or sigmoid or some sort of nonlinearity, are linear here, and instead we insert the nonlinearity in the spatial decimation, the pooling that takes place in a convnet. We do it by taking a product of neighboring pixels, and that's how we insert an important nonlinearity that gives the network its strength and makes it practical in practice. But from a theoretical perspective, this network has the good trait that it could be written in this clean form as an inner product between two tensors. Now, for those of you who aren't familiar with tensors, so basically they're high-dimensional arrays. If a matrix has two indices and it's a two-dimensional array, you can imagine a tensor which has n indices as some sort of a high-dimensional extension of that with an exponential amount of entries. So that's in general, and our network, this convolutional network, can be written as some sort of a rank 1 tensor. It's pretty simple, and I won't go into it. That's related to the inputs to the network. But there's the important tensor here that's called the convolutional weights tensor, which really holds all the information regarding the network calculation over its inputs. And its entries can actually be computed given the convolutional weights of the network. So you can take a convolutional network, and you make some computation. It's a polynomial, and to achieve this tensor. Okay, so this form would be very related to many-body quantum wave functions, as we'll soon see. Just to quickly introduce, there's a similar class of recurrent arithmetic circuits. It's a circuit of RNNs, and we use multiplications instead of the common nonlinearities. And again, we receive this clean form that this RNN has a function that's just an inner product between two tensors with a recurrent weights tensor holding all the information really regarding the network structure and computation. Okay, so these two networks, we're going to show some equivalence between them and many-body wave functions. So a quick intro just for our needs, we're going to refer to a many-body wave to a quantum wave function as a vector in a Hilbert space. Notation-wise, whoever has a BSc in physics knows this ket notation. So it's just a vector. And by specifying some orthonormal basis to the Hilbert space, the coefficients vector tells you everything there is to know about the wave function, which in turn fully describes the quantum particle's quantum state. And when extending this to many quantum particles interacting, then the Hilbert space with which the many-body quantum wave function resides in is an outer product of the single particle Hilbert spaces. And really what's the takeaway here is that the many-body quantum wave function is fully specified by a coefficients tensor. So if you know that tensor, you know everything there is to know about the quantum system. Now, we had a tensor that described the convolutional or recurrent weights tensor, the convolutional recurrent network fully. And what we do is, by hand, we just define many-body quantum wave function by these tensors, the convolutional or recurrent weights tensors, to gain some equivalence, an exact equivalence between the function realized by these convnets and RNNs to some inner products between two wave functions, with the coefficients tensor of the wave function being exactly equal to the weights tensor of the convnets and RNNs. So this equivalence will allow us now to transfer tools and results between the two domains in the following way. The first is the notion of quantum entanglement. I won't go into definitions, but broadly speaking, entanglement between two subsets of a system of n particles between A and B is the amount of quantum information that's stored inside of each subsystem with respect to the other. And this is a quantity that's fully specified by this tensor, by the wave function's coefficients tensor. So by some rank measure over this tensor with respect to the indices, for example, you take the left particles are in subsystem A and the right in subsystem B. So you take some sort of rank of this tensor with respect to this partition, and it tells you how entangled or how much information this wave function really holds, which mixes these two parts. What we showed is that previous means of quantifying information that a convnet can model with respect to its inputs, called the separation rank of the network, is exactly equal to an entanglement measure of the wave function that we defined. So previous means was the distance from complete multiplicative separability. So a multiplicatively separable function is one which just models a function times, for example, the left side of the image, times the function over the pixels in the right side of the image. And we've shown, and the distance from this separability was was used in previous works in order to quantify the network strength relative to a certain partition. And we showed that entanglement with respect to this partition is exactly equal, so we now can discuss the network's ability to correlate subsets of its inputs through this language of entanglement. So this brings forth really practical rules of thumb. If we have, for example, a symmetric face image like here on the right, so it's obvious that for such symmetric face images, the right and left parts of the input are correlated. For the right and left cheeks have the same structure and so on. So it's advisable that the network models some function that reflects high dependencies between left and right. And now we say that if the corresponding tensor induces low entanglement with respect to this left-right partition, then the hypothesis space is limited. The network cannot model the required functions for this task. In the RNN case, we highlight a different partition. We call it the start-end partition. And we say that it's a surrogate for a long-term memory of an RNN, which is obviously a required trait. Because here, if the network only models separable function with respect to this start-end partition with low entanglement, then it's probably going to predict that someone slept on the bed, because that's where people sleep. But if it's able to take into account the fact that a cat was mentioned in the first half, then it's probably going to predict rug, because cat sleeps on rugs. So here the start-end entanglement is a surrogate for the long-term memory capacity of the network. And this is a motivation slide for what we would like to happen. And we now take inspiration for how physicists control entanglements in their networks in order to derive rules of thumb for deep learning practitioners of how to tailor their network architecture with respect to specific task specification. So the tensor network tool used in physics is used in a very principled way. It's very the opposite of how the cliche of deep learning practitioners who just throw a network at a problem. The physicists quantify the entanglement of a given many-body system, and then they choose from a menu of tensor networks the network that best corresponds to that entanglement. So we would try to mimic that. I'm just going to quickly say that a tensor network is a weighted graph where each node is a tensor and the edges correspond to the indices. So a matrix is a node with two edges, and an n-order tensor is a node with n edges. And it's just a general, you could view, when you see a large tensor network in the next slide, you could just imagine it's a generalized matrix multiplication to more indices than two. So what we did is we cast the computation of a convolutional network as a tensor network, where the weights in this weighted graph are exactly the number of channels per layer that are in the network. So in the first layer we have R0 weights. In the 0th layer, that's the number of channels in the 0th layer, the amount of feature maps that you choose to put in your network, and so on. We also cast an RNN as a tensor network, and our first result really quantifies the connection between the tensor network architecture, which translate exactly back to the convolutional network architecture, and the information that the network models with respect to its input. So what we showed, we adapted a result from quantum physics about the connection between entanglement and tensor networks, and we show that we can control the entanglement of a network by controlling the minimal cut of a certain partition that separates the partition size. So we take the example of, for example, the left and right partition that corresponds to longer ranged correlations, and we see that in order to separate them, we need to make a cut in deeper layers, whereas the interleaved partition here on the left corresponds to shorter range correlations. We see that edges from earlier layers must be involved in this minimal cut that separates the two sides of the partition. So this gives us a corollary of the theorem that deep layers are more important for longer range correlations, and earlier layers are more important for shorter range correlations. And this really gives practical rules of thumb when we have, for example, blown up MNIST digits, and we need some sort of a longer range dependency to be modeled here, then a network with more parameters in deeper layers does better on the task than a network, the green network, with more parameters in earlier layers, and vice versa for a local task with very small images. a network with more parameters in earlier layers outperforms a network with later layers, and this can be translated to a practical task. For example, a task of identifying faces in a security camera at the airport. Then the faces to be identified are going to appear small on your screen. So you need to invest more parameters in earlier layers, according to this theorem. And this is one corollary. I'll quickly, so it's a way to tailor the architecture for a given task. I'll mention a result on RNNs. So the start and entanglement that I mentioned earlier quantifies is a measure of long-term information captured by the network. And for shallow RNNs, our tensor network was this network on the right. And in order to separate the start and the end here, we see that one cut is needed. This really implies, our theorem implies that the long-term memory of just a shallow vanilla RNN trivially increases linearly with the number of parameters. So if you want more long-term memory, just invest more parameters. But a common practical choice that gives good practical results is to stack RNN layers, to have a deep RNN. And when we draw the quantum tensor network equivalent of a deep RNN, we show a more convoluted network, which allows us to prove that for deep RNNs, the long-term memory capacity grows polynomially with network depth, whereas a shallow one is upper bounded by a linear term, which means that deeper recurrent networks have much better long-term memory, which actually we have a conjecture that it increases with depth. So this is the first result regarding the relation between an RNN's depth and its memory that's derived by these quantum physics tools. Now I'll briefly mention towards the end our contribution to the other side. So without going into details, we proved that convolutional networks are extremely fit for currently unsolved quantum problems of highly interacting quantum particles, and that they actually have they're polynomially more efficient than any other existing approach used today in the quantum physics field. We showed that deep learning has the potential to provide access to unattainable quantum phenomena. But when we tried to implement it, we saw that people in the field are aware of deep learning, but they face an optimization hurdle where their methods limit convolutional network sizes to ridiculous sizes. If it's more than 1,000 parameters, they can't really optimize their networks on the quantum problem. And we borrowed tools from Pixel CNN, if you guys autoregressive tools, and we were able to improve the sampling there, and we applied the first competitive size convnet on a quantum problem and achieved the most exact results on that benchmark. And we're now looking to better this contribution to unsolved problems in the quantum domain. So just to sum up, we've drawn some analogies between convolutional recurrent networks to quantum wave functions, and we use entanglement as a measure to model dependencies that a network models with respect to its inputs. And we induce some rules of thumb regarding how to tailor the architecture for given task dependencies. And we also showed a first of its kind result regarding the memory in RNNs. We're now trying to make contributions in the other direction towards physics. Thank you very much. Yeah, it's a good question. So there was a question whether about the ability to reach the entire Hilbert space. So obviously, no, it's a small manifold there, which is induced by the network architecture. And you ask how playing with different traits of the network, its depth, number of parameters per layer, and other choices you make, how that changes the properties of the manifold that you're accessible to in good resources and efficient resources.